today's video is going to be a titration involving a strong component and a weak component. So the setup here is going to be very similar to the type of setup that we saw in class for a strong titration. Now the example we're going to be looking at is example number 5 in your handout for chapter 19. And in this particular situation, what we're going to have is a flask or sample containing 20 milliliters of 10th molar butyric acid, HC4H7O2, which has a Ka of 1.5 times 10 to the minus 5th as given in the problem. Now, we're going to be titrating that with a strong base, which is going to be 10th molar NaOH. So the idea here is that we're going to be adding various volumes of the strong base to the weak acid, and we're going to be calculating the pH after each addition. So part A actually asks us for the concentration, or rather the pH of the acid solution before we've added any base. We're not going to do that one because that's just a simple acid dissociation problem involving a weak acid, which you already know how to do. So what we want to do is work our way into the problem so that we can see what starts to happen as we add the base to the acid. So part B here says that we're going to add 10 milliliters of the NaOH solution to the existing acid solution. So as we did in class, the first thing that we want to do is to calculate the number of moles of each component that we've got at the outset of the problem. So we can calculate the moles of the NaOH by taking the volume, which is 10 milliliters or 0.01 liters, multiplying that by the concentration of the base, and we end up getting 0.001 moles of the base. Likewise with the acid, we're starting out with 20 milliliters of it. That's the same thing as 0.02 liters. We're going to multiply that by the concentration of the acid, and we get 0.002 moles of the acid. So at this point, we can actually see where we are in the titration. I have not added yet enough moles of base to react with all of the moles of the acid, so we know that we are before the equivalence point. So at this point, what we want to do is write down the actual reaction of the acid reacting with the base. All right? So we know that the acid is HC4H7O2. Here it is right here. We're adding base in the form of hydroxide from sodium hydroxide dissociation to that. So this is the actual reaction that's going on in the solution. Now if we take a look at this, what we see is that we have a weak component here. That's the weak acid. And we have a strong component. That's the strong base. Now you recall from class in previous videos where I've told you that if we have a weak component reacting with a strong component, we can assume that that reaction has a very large K associated with it. You can verify that for yourself. Now, weak plus strong then goes 100% to the right. So what we see here is just a simple Bronsted-Lowry acid-base reaction where the acid will protonate the base to give us water, and we're also going to make the conjugate base of the original weak acid. That's the C4H7O21- ion. All right, so now what we need to do is we need to start filling in numbers into our ICF table. Why do we use an ICF table here? Because the reaction is assumed to go 100% to the right. All right, that being said, let's go ahead and stick our moles in. Now remember, we can use moles in ICF tables. If we're doing ice tables, we have to use molarities, but we'll use moles here to keep things simple. All right, so the moles of the acid turn out to be 0.002. And the moles of the base are going to be half that, 0.001. All right, we've not made any water, and we don't worry about the water anyhow. And we haven't made any of the butyric ion, which is going to be the conjugate base. So this reaction has to go to the right. Now we know it's going to go 100% to the right, so we have to look for a limiting reactant. Looks like our limiting reactant is going to be hydroxide. So we're going to lose 0.001000 moles on our reactant side, and we're going to gain that amount on the product side. All right, add down as we normally would. We're going to be left with 0.21000. So we're left with 0.001 moles of the acid. We're going to not have any of the base left, and we're going to have 0.001 of the anion of the acid there. All right, so if we look at this, what we're going to see is that we actually have here something that looks like a buffer. You ought to be able to recognize this as a buffer solution. Why would it be a buffer solution? Well, because what we have here is a combination of a weak acid and its conjugate base in solution. So technically at this point we could use Henderson-Hasselbalch to solve this problem, but we won't. I'm going to use full-blown equilibrium to do it. All right, so what we have to now do is convert these species from the F line over into the I line of an ice table. But before I do that, remember I have to convert moles to molarities. So I need a total volume to do that. So our total volume in this case is going to be the 20 milliliters of the acid plus the 10 milliliters of the base, which is 30 milliliters, or 0.03 liters. So now, to convert over to my ice table, what I have to do is I have to take my moles of each species that I have here. I have to divide the moles by the total volume, and those are the numbers that are going into the I line of my ice table. But now the question is, what ice table do I want to use? Well, at this point, I'm going to treat this kind of like a common ion effect problem like we talked about before. So what have I got? I've got a mixture of a weak acid and its conjugate base. So I'm just going to let that weak acid dissociate in water in the presence of its conjugate base. So that means I need to use the Ka relationship for that acid. So if we look over here, we have exactly that reaction set up. All right, so now we're going to use an ice table. We're defining this with a Ka because, again, what we're talking about is a weak acid dissociating in the presence of its conjugate base. So let's put those numbers in. For the acid, I need 0.001 divided by 0.03. And I've done that. You get 0.03333 repeating. That's a molarity now, so I'll put a molar there just to remind ourselves that's a molarity and not a number of moles. Water we don't worry about. Hydronium ion, have we made any of that yet? No, we haven't. But I do have a concentration of the conjugate base. That's 0.001 moles divided by 0.03 liters as well from the prior table. So in this situation, I have the same molarity. Now I'll write that with an M just to show again that's a molarity. And again, those numbers come from the F line of the previous ICF table divided by the total volume. Now the reaction has to go to the right. All right, so I have 0.03333 minus X. I got X, and I got 0.03333 plus X. All right, plug everything into the law of mass action. We get X times 0.03333 plus X divided by 0.03333 minus X. And all of that's equal to the Ka, which I gave you in the problem. That's 1.5 times 10 to the minus fifth. All right, so how do we simplify? We can get rid of additive and subtracted x's. And now you can see the math gets easy because I can cancel out these two numbers. And I can say that x now equals 1.5 times 10 to the minus fifth. So now, remember, that's hydronium ion concentration. So now it's easy to get a pH for this. So the pH is just going to equal to the negative log of 1.5 times 10 to the minus fifth. And I've worked that out. That pH to 2 sig figs turns out to be about 4.8. So what we see here is we still have an acidic pH, and that's because the acid is still in excess. We have not reached the equivalence point of the titration yet. All right, so we're back to do part C of this particular problem now. So in part C, what I'm going to be doing is I'm going to be titrating the very same acid solution, but now I'm titrating with 20 milliliters of my titrant, which is going to be 10th molar NaOH. So again, the very first thing that we want to do is we want to calculate how many moles of the acid and the base we've got. So you know how to do this calculation now, so you can verify, if you wish, that I'm going to end up with 0.002 moles of my acid and 0.002 moles of my base. And what we see here at this point in the titration is that the moles of the acid are equal to the moles of the base, so that tells us that we are at the equivalence point in the titration. The moles of the acid are equal to the moles of the base. So again, let's see what happens from a chemical point of view here. We're going to actually write the reaction that's actually happening in solution, and this is the very same reaction that we used in part B, where I have the acid reacting with the base. And we see here again that this is a weak situation, reacting with a strong, and what we get is weak plus strong goes 100% to the right, so we use an ICF table. So again, putting my moles into the I line here, what I'm going to find is that I'm going to have 0.002 moles of each component. I've not made any of the conjugate base yet. And if we look at this now from the point of view of a limiting reactant problem, we see that both the acid and the base together are limiting reactants. So we're going to use up both of them, leaving us with 0 moles of each one. However, since we get 100% conversion, we see that we're going to end up with 0.002 moles of the conjugate base, the C4H7021-. So now what we have to do is think about how we're going to set up our ice table to be able to now calculate the pH of the solution. So we have to look at our ICF table and ask ourselves, what have we got after this reaction has taken place? And what we have is nothing more than some number of moles of the conjugate base. So now to calculate the pH of the solution, what we have to do is look at the dissociation of the conjugate base now on its own in water. All right, so that's what our ice table is going to consist of. Again, this is a very, very important point to understand. I don't have any of the weak acid left. I don't have any of the titrant left. The only thing that's left in my solution at this point is going to be the conjugate base of the original acid. So that's the only thing left that can react with water to generate hydroxide ion to generate a pH. All right, so we're going to look at that ice table over here. All right, so looking at the ice table now, again, just to reiterate, what we have now in our ice table is just the dissociation of the conjugate base of the original acid in water. Why? Because that's the only thing I've got left in solution at the end of the ICF table. So that reaction is governed, of course, by a Kb. Now again, this is a molarity. I know that because I'm using an ice table, and I know that I have to put molarities into ice tables. That number came from the 0.002 moles of the conjugate base divided by the 0.04 liters total volume of solution that I now have. All right, so at this point, we're going to work this as like a regular old ice table. We know that the reaction has to go from left to right, so I've got a minus x there, an x here, and an x here. Now I know I'm 0.050000 minus x, and then I've got x and x. Now here's the issue. This is not a Kb that I can look up, but I know the Ka of the conjugate acid. So we know now how to get a Kb for a weak base that comes from a particular conjugate acid. So we know the relationship, Kw equals Ka times Kb. I can solve that relationship for Kb, and I can put in my Kw value and also the given Ka value for the conjugate acid. And from that, I get a Kb of 6.7 times 10 to the minus 10. So now that's the number I want to use for my K from my log mass action. So getting down to log mass action, I've got x squared over 0.05 minus x. And that's equal to my new Kb, which is 6.7 times 10 to the minus 10. All right, simplify. Pull out that subtracted x. Now you guys should be able to verify that I can solve for x. And when I do that, my x turns out to be 5.8 times 10 to the minus 6 molar. Now, what does that correspond to? That corresponds to, of course, the hydroxide ion concentration in the solution. So at this point, we have to calculate a pOH. Again, you guys know how to do that. My pOH, which you can verify, turns out to be 5.24. And from that, I can get a pH by subtracting from 14. And when I do that, the pH turns out to be 8.8. Now again, the important thing to recognize when we do this is that we are at the equivalence point of the titration. However, what we will see is that we no longer have a pH of 7 at the equivalence point like we had in the case of the strong acid, strong base titration. And the reason for that goes back to our ICF table. And again, what we recognize at the equivalence point is that we don't just have water there, which is neutral. What we now have is some concentration or amount of the conjugate base of the original acid in solution. And as a result, that's going to push the pH above 7. So in this particular case, when we have a weak and a strong situation, we will never have an equivalence point of 7. So that's an important thing to recognize. All right, folks, let's take a look finally at part D of this problem. And in part D, what I'm doing is I'm titrating the original acid with 25 milliliters of the 0.1 molar NaOH. So again, we're going to calculate the number of moles of both acid and base. And what I now see in this situation when I do this is that the hydroxide ion now goes into excess. So we're beyond the equivalence point in the titration. Now, how do we calculate the pH of the solution at this point? We're going to go through the same process that we did before. So again, very same reaction that we've used. This is the actual reaction occurring between the acid and the base in solution. And in this case, if you work your way through the ice table, again, you're going to see that the acid now becomes the limiting reactant. All right? So at the end, in the F line here, what we're going to get is no acid left, but we do actually have some moles of the hydroxide in here. We've also generated some moles of the conjugate base as well. So now what we want to do is we want to plug these values expressed as concentrations back into the ice table. And again, the ice table is going to be in terms of the dissociation of the weak species that we have in solution, which in this case has to be the conjugate base, because again, I don't have any of the conjugate acid left. So now we're going to make our way over to the ice table that we talked about. Again, what we're doing is we're plugging in concentrations, where I'm going to take each one of the mole values from the F line in the ICF table, and I'm going to divide that by the total volume, which in this case is 0.045 liters. So you can now verify, based on that total volume, that this is the concentration of the weak base that I get, and this is the concentration of the hydroxide ion that I start with. Again, both of those values came from the F line of the previous ICF table, adjusted to concentration. So if we work through our ice table, we see that the reaction, again, has to go from left to right. So we're going to lose X on the left, we're going to make X for each component on the right, and we'll end up with an E line that looks like this. So now, this is easy enough to solve. Again, plugging everything back into the law of mass action, using the Kb that we calculated previously for this particular conjugate base of the original acid. What we can see now, by getting rid of additive and subtracted x's here, is that X now becomes 2.7 times 10 to the minus 9th molar. Now that's a very, very tiny concentration. Now to get at pH, what we have to do is we have to go by way of pOH, which of course involves the total concentration of the hydroxide ion that we've got at equilibrium. Now if you look at this, we have to take this little tiny X here that we got, and we have to add it to the concentration of the hydroxide ion that was left over in the previous ICF table. All right? So when we make that addition, what we see is that this is a negligible amount of hydroxide ion. So to get the pOH, all we're going to do is we're going to take the negative log of the original hydroxide ion that we had in excess, expressed as a concentration. And when we do that, we get 1.95, and from there we can calculate a pH by subtracting that number from 14, and we get 12.1. So the take home here that we have is that once the strong thing goes into excess, we don't really need to worry about any subsequent dissociations involving any other weak species. All we have to do is work from the standpoint of the concentration of the excess strong component, then to calculate the pH. So that pretty much wraps up a typical sort of strong, weak titration problem. And we'll do more practice with this in class. See you next time.